Unit 5, probability distributions. Picking up with standard 16 here to start second semester, which focuses on a couple of specific kinds of probability distributions. What's called the geometric probability distribution, and later this week we'll get into what's called the binomial distribution. A couple of specific types of probability distributions. They each involve what are called Bernoulli trials. Bernoulli trials have these three criteria here to the left. A Bernoulli trial is a specific trial, a specific event, with only two possible outcomes. Either you do or you don't. You succeed or you fail. It happens or it doesn't. You make the shot, you miss the shot. You draw the card, you don't draw the card. You either do it or you don't. Succeed or fail. Do no trial. The probability of success is the same for each trial. The probability it happens remains the same for all the different events within the trial. And then each trial is independent. Bernoulli trials are the events of the distribution and the distribution. So it's criteria for each of the two. All right. So the specifics for the geometric distribution here to the right. The geometric distribution is a specific probability model for how many trials it takes until the first success is achieved in a sequence of Bernoulli trials. How many different trials will it take before the first success? You're going to fail, 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 and then the last attempt is the first success. How many different times do you have to do something before you do it correct? That is what the geometric distribution probability is. Some notation here. I'm going to let P be the chance of success, the probability of success. And Q would be the probability of failure. If there's only two different outcomes, I just the probability of failure to 1 minus P. There's a 60% chance of rain. There's a 40% chance that it doesn't rain. Just 1 minus that 60%. P is going to be success. Q is going to be failure. This is a random variable. So we're going to let capital X denote the number of trials until the first success, like the distribution talks about. Our probability model, the probability that capital X equals lowercase x. Remember this lower, oh, you know where you see that? Yeah, sorry, we switched seats here for semester. You are at table. London, you can join them here. X number of attempts till the first success is equal to Q to the X minus 1. So I fail X minus 1 times. If it takes me 4 trials till the first success, don't I miss it on the first 3 attempts? For example. So this Q is first success only once on the last attempt of the trial. The average number of attempts before the first success, the expected number of attempts before the first success is equal to 1 over P. The standard deviation in that average, sigma of X, is equal to the square root of Q over P squared. So there is the measure for center and spread in this distribution. We have the probability generator, Q to the X minus 1 times P, and then the center and spread for the distribution. The center or expected amount is 1 over P, and the standard deviation in that average is the square root of Q over P squared. So let's look at a couple of different questions based off of those information. All right. We're going to roll a dice. I want to roll a 1. What is the chance that the first time I roll a 1 happens on the 4th roll? Is this a Bernoulli triangle? What are the 2 possible outcomes? In questions. If I want to roll a 1, what are the 2 possible? Or I don't, right? I hit the 1 or I don't. I roll something else. So only 2 possible outcomes, success or failure. That looks like it's right. Is the chance that I roll a 1, is the chance of success the same for each roll of the dice? Yeah. Every time I roll the dice, I have the same probability of rolling a 1, right? I'm just running through these conditions of a Bernoulli triangle. Affected by any of the previous rolls. Now, if this is not true, then this wouldn't be true of all either, right? Wasn't independent, the chance of rolling 1 would change after each roll. Those kind of go hand in hand. All right, so what is the chance that the first time I roll a 1 when rolling the dice is on the 4th roll? Four rolls to roll a 1. What happened on the first 3 rolls? Got a 1. So that's kind of like the q to the x minus 1 part of the formula. I missed rolling a 1 3 times because it takes me 4 rolls to roll a 1. What's the chance, what's the probability of not rolling a 1? How many numbers aren't 1 on a dice? So it's 5 out of 6 to the x minus 1, or 4 minus 1, which is 3. I don't roll a 1, I don't roll a 1, I don't roll a 1 for the first 3 times I roll the dice. What happens on the 4th roll? I do roll a 1. What's the chance that I roll a 1? 1 out of 6. So there's the probability in question. So type that into a calculator. 5, 6 to the 3rd. Times 1 out of 6. It's about 0.0965. Less than 10%. Then 4 rolls to roll a 1 on a dice. How is this question different than the one that we just answered? Takes less than the dice. On the first or the second or the third. So I need to combine the probabilities of each of those 3 different dice. Getting the 1 for the first time on the first roll of the dice, the second roll of the dice, and the 3rd roll of the dice. The probability of x being less than 4, the first time rolling the first 1, is less than 4 attempts, is the sum of the probability of getting it on the first roll, p of x equals 1, plus getting it on the second roll, and getting the first 1 on the 3rd roll. Happens. 1 out of 6. Do I miss the first? Do I miss getting a 1 at all? Do I fail at all? So it's just 1 out of 6. Getting the first 1 on the second roll. If I get the first 1 on the second roll, how many times do I not get a 1? How many times do I fail? once. So that would be 1 out of 6. I missed the 1 on the first roll, I get the 1 on the second roll. So 5 6 times 1 6. Getting the first 1 on the third roll, what happens on the first 2 attempts? I would have had to have missed. So I missed twice. 5 6 times 5 6, or 5 6 squared. 1 6. I got the 1 on the last roll. 6 plus 5 6 times 1 6. 5 6 squared. Looks like about 0.4213. Rolls to roll a 1 on the dice. What's the chance that it takes 3 or more rolls? How is this question different than any of the ones we've done so far? Greater than 3, so it could be 3 or higher. I could have gotten the 1 on the third roll, the fourth roll, the fifth roll, and so on. It just can't be what? 1 or 2. So let's think about this using complementary events. Let's think about this working backwards. The probability that getting the first 1 on the third or higher roll is 1 minus 2 1s it can't be. I take the sum of every outcome, 100%, and exclude the 2 I do not want to have for my value. The 2 I do not want to include as a part of my answer. 2 that it can't be. It takes 3 or more rolls to get the first 1, so I could not have gotten it on the first or second. Joey, you are, is that right? Yep. So let's see here. 1 minus 1 6 plus 1 6. We've used those 2 before. That's approximately 0.6944. Just about 70% chance that it's going to take 3 or more rolls. There's an infinite of things because it's either 3 or higher. So think about it backwards. Take away the 2 that it cannot be from the sum total of 100%. Last one, find the average number of rolls before rolling the first 1. So I need to find the expected number of rolls, the average number of rolls, that's 1 over p. And the standard deviation in that average, the standard deviation is the number of rolls before rolling the first 1. The square root of q over q squared. P is the probability of success, Q is the probability of failure. So that's the same 1/6 and 5/6 we've been using. The expected or average number of rolls before rolling the first 1 is 1 divided by 1/6. 6. If there's 6 numbers on a dice, should I expect 6 rolls before getting any particular number? In this case, the first one. Of course, there's randomness here. There's some variability. So what would be the standard deviation in that expected number of rolls before getting the first one? That would be the square root of 5/6 divided by 1/6 squared. All right, so the square root of 5/6 divided by 1/6. A lot of variability with a standard deviation that high compared to the average number of rolls of 6 rolls. All right, let's do this. Let's get some practice pulled up. Why don't you go ahead and grab your laptops and dig into what's on Schoology.